To this video. In this video, I'm going to be talking about the implementation of the Minimax, alpha beta, and the WalkSat algorithm. Now here we can see that here there's a class that is game that is implemented. It's just the bare bone structure on how we can extend this to the what is that? The 2-ply and the 4-ply game for the application in Minimax and the as well as the alpha beta pruning. So let's see how it is working. Yeah, let's see the fig 5.2 of the textbook that extends the game class. Now here we have a dictionary. All the nodes or the 2-ply game tree has been depicted as a dictionary. So here we have a dictionary that is has connections to the preceding nodes. Now, for example, A is connected to B, C, and D. If we take a look at that, so here we have A, it's connected to B, C, and D via A1, A2, A3. So the same thing is implemented here. So A is connected to B, C, and D via A1, A2, A3. B is connected to B1, B2, B3 via B1, B2, B3. You get the idea, right? So that's so on and so forth. All right. Now, obviously, B, C, and D is all taken care of. Now, the utility function is also a dictionary that takes in the node and gives the corresponding value. Now, here B1, B2, B3, C1 to C3, D1 to D3 are all the terminal nodes, which have the values 3, 12, 8, 2, 4, 6, 11, 5, 2 respectively. So the same thing has been implemented. Is it 11? Sorry, 14, 5, 2. Yeah. So 14, 5, 2 respectively. Now here we have set the initial state as A, and then we are checking if now the next thing is to see which of these nodes are are the min node or the max node. Here for instance, A is the max node, and these terminal nodes, I mean, this is just a 2-ply game, but if we were to extend this, these last terminal nodes would have been again the max, right? So A here is max, B, C, D min. Again, these terminal nodes would have been max. So the same thing has been told here. So now if the state is in B, C, D, give me the min, or else just give me the max, and based on that calculate my utility value, right? All right, so that is so far so good. Now you've also asked us to implement a 4-ply game tree, wherein we have 4 different turns. So first is max, next is min, again next is max, and then next is min, along with their final terminal nodes or the utility values. Now here the same has been implemented. Now A is a dictionary, obviously. Again the same pattern is going to follow. It connects to B and C. Now B connects to D and E, so on and so forth. If you just trace the dictionary, we can know how it is working. I will also post the this to a 4-ply game tree in the GitHub's README, so that you can see the game tree in itself, the pictorial representation of it. And these are the utility functions. Those are the terminal nodes. All right. So now out of these nodes, which are all the min nodes and which are all the max nodes? So the min nodes are B, C, H, I, L, M, and O, and anything if the state is in any other node apart from these, just return the max and then calculate the utility value based on those. And these are the utility values. All right. Now let's go ahead and implement the min max. Now I'm just calling game equal extended equal to the fig. I'm just instantiating the extended class, and then I'm going to run min max on any node. So that gives the minimax of the E. Now we can see it is E1 because now if we take a look at the value E1, where is it? That should be in E, right? Yeah, E1 is J, and then J values, yeah, see, J1 1, right? So it makes sense why it took E1. So it is optimized for, and now keep in mind that this is max, so it makes sense why it took J1, because J1 is 1 and J2 is minus 43, so obviously 1 is greater, so that is why it is E1, if we recursively see that. Now again, we can put any input, any state, and it will give the min max value respectively. Now let's instantiate the base class, or the just fig 5.2 class, which is just the implementation of that of the book. So now let's say I want the min max of C. That should be C1, because now we are trying to optimize for the minimum, right? The minimum state. So what is the minimum here? In 2 and 4, 6, 2, 4, 6. Obviously it is 2, so that's why it's giving us C1. So any other state I give as an input, it'll give the output. Even this. So let's say I give the state O. It should, yeah, it's O1. So here now, just to make sure, okay, I'll give the state that is max, just to you know now let's say which is max. J is J in max? No, J is not in max, so I'm going to give, it should optimize for um, the maximum. Again, it's J1. Obviously that's E1 and J1, they are the same. Now let me take another node, that is K, not in the min. So that is K2. Now if we take a look at the value of K2, so K1 is minus 75, K2 is 49. So right off the bat we know it is getting us the optimal value. Alright, now the same thing is implemented with the alpha beta pruning. Now I'll pass in the state and the extended game, the 4-ply game, and it is giving out the optimal value. So B is the minimum node. So if we take a look at the value for B, um, B is D. Well, recursively it keeps going, right? So I mean, now you get the idea, professor. So again, to trace it is going to take some time. It keeps going and finally it reaches those nodes, and then whichever is the minimum in this case will be taken off. So B2 it says. So all right, now let's go ahead with the implementation of the WalkSat algorithm. That takes in different clauses, the probability and the maximum flips. So now again, now we have to run this on the CNF version of the sentence, right? So that is what this is doing. So it takes the WalkSat and applies the conjugates to convert it to CNF, and then the sentence that we pass in. Now let me go ahead and run the WalkSat algorithm. Now these are the different literals x1 to x6 that has been represented using the expr function that is given to us by the AIMA GitHub repository. Alright, so now let me just implement. Now here we can see the different sentences, right? So here these are the different 3 randomly generated 3 CNF sentences of 10 different of them. Now here we can see this first sentence. So x1 or x2 or x3 and not x1 or not x2 and x1 or x3 and x2 or x3 sorry, not x2 or x3 and x1 or not x3. So the same thing, whatever is here, just has been put in form of expression as in the different literals. And then if we run the WalkSat algorithm on that with probability 0.5 satisfiability, it gives us the values of different values of the different literals. Now obviously I've done all of these for 10 different sentences. Now in order to see how much time it takes, I've used the timeout function of the Jupyter notebook. So this will run for 100 different loops, and then it'll give us the average time it took to run the function, so we can see how much time it takes. Alright, we see that it has taken about 16.3 millisecond with plus or minus 233 microseconds. That is kind of negligible. It has done 7 different runs with 100 loops each. Alright, so we understood, right? So we kind of have the implementation. And this is a Jupyter notebook. I'll upload this to my GitHub repository and the link of the video that I've also taken the screen record of. Yes, professor. So that is pretty much it. And I'll also give the references to make sure to give the references. But yes, professor, that is pretty much the implementation of the Minimax, alpha, beta, and the WalkSat with different 4-ply game tree. Alright, professor. Thank you very much.